Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're starting a new topic in chemistry, and that topic is acids and bases. Now I know this topic can seem like a lot at first, especially once we start getting into things like equilibrium, Ka and Kb values, and titration curves. But I don't want you to worry about that. We're going to build up to that very slowly, and we're going to start with the most fundamental question of all today. What is an acid and what is a base? Over the past century, chemists have proposed different definitions for acids and bases, with each one expanding on the previous to include a wider range of chemical behavior. The goal for today is to walk through these three major definitions: Arrhenius, Bronsted-Lowry, and Lewis, so we can understand what counts as an acid or a base in each case, and how they relate to one another. Once we've built that foundation, we're going to be able to handle all of the acid-base reactions to come. Let's begin with the earliest definition of acids and bases. This was proposed by Arrhenius in the late 1800s. According to the Arrhenius definition, an acid is any substance that increases the concentration of hydrogen ions when dissolved in water. In practice, these hydrogen ions don't exist freely for long, and they quickly associate with water molecules to form hydronium ions. This is written as H3O with a +1 charge. That's why we typically represent the reaction in terms of hydronium rather than hydrogen ions alone. So let's take a generic acid written as HA. This is going to donate a proton to water to then form hydronium ions, and it's going to leave behind its conjugate base written as A with a -1 charge. In contrast, an Arrhenius base is defined as a substance that increases the concentration of hydroxide ions in solution. Hydroxide ions are written as OH with a -1 charge. So here, a base B reacts with water to release hydroxide ions and form its conjugate acid, which is written as HB with a +1 charge. This definition is super straightforward, and it works really well for common strong acids like hydrochloric acid or strong bases like sodium hydroxide. However, it has significant limitations. It only applies in aqueous solution, and it only includes substances that will directly produce hydrogen ions or hydroxide ions. So as a result, it excludes many reactions that we now recognize as fundamentally acid-base in nature. So to address the limitations of the Arrhenius definition, chemists developed a broader and more powerful framework known as the Bronsted-Lowry definition, which is what we're going to work with in our course. In this model, an acid is defined as any substance that donates a proton, and a base is any substance that accepts a proton. That's it. That's the core idea. And what makes this definition so useful is that it doesn't require the presence of water, and it doesn't depend on the production of hydroxide ions. It's entirely centered on the movement of protons, which allows us to describe acid-base behavior in a much wider range of chemical systems. So let's begin with a Bronsted-Lowry acid. This is going to donate a proton to water. So in this case, the acid HA donates a proton to our water molecule H2O. The proton transfer turns water into hydronium, and in the process, HA becomes the conjugate base A with a -1 charge. This leads us to a really important idea, one of the most important ideas in Bronsted-Lowry acid-base theory, and that is that acids and bases always occur in pairs. So you start with an acid and a base, and after the proton is transferred, you're left with a new acid and a new base. These are called conjugate acid-base pairs, and they're directly related to each other by the gain or loss of a single proton. So here, HA is the acid, and its conjugate base is A with the -1 charge. Water is the base, and its conjugate acid is hydronium. Now let's look at the other side of the definition. A Bronsted-Lowry base is any substance that accepts a proton. In this reaction, we start with a base, which we'll call B, and it reacts with water. Here, the base accepts a proton from water. That turns the base B into its conjugate acid, which we write as HB with a +1 charge. And it leaves behind hydroxide ions, which come from the water molecule. So this reaction shows proton acceptance, not donation. B is the base, HB +1 is the conjugate acid, and water is now acting as the acid because it gives up a proton. Now, let's move on to the broadest definition. That's going to be the Lewis acid-base theory. This one doesn't focus on protons at all. Instead, it is based on the transfer of electron pairs. So a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. So in this framework, a molecule like boron trifluoride, which has an empty orbital and can accept a lone pair of electrons, that is considered a Lewis acid. Meanwhile, a molecule like ammonia, which has a lone pair of electrons that it can donate, it's considered a Lewis base. So the Lewis definition is considered the most general because it captures all of acid-base interactions that involve electron pair movement, including a lot of reactions that don't directly involve protons at all. In our course, again, we're going to be focusing on Bronsted-Lowry acids and bases. But if you're wondering how these definitions relate to each other, here's a good way to think about it. The Arrhenius definition is the most narrow. It only applies to acids and bases in water. The Bronsted-Lowry definition is more broad because it applies to proton donors and acceptors in any solvent. And then the Lewis definition is the most inclusive of all because it includes any electron pair exchange, whether or not protons are involved. So we can say every Arrhenius acid is also a Bronsted-Lowry acid, and every Bronsted-Lowry acid is also a Lewis acid, but not every Lewis acid is an Arrhenius or Bronsted-Lowry acid, and the same goes for bases. One thing worth highlighting here is that some substances have the ability to act as both an acid and a base depending on the chemical environment they're in. These are called amphoteric substances. And the term amphoteric means that a species can switch roles. So in the presence of a strong acid, it behaves like a base, and in the presence of a strong base, it behaves like an acid. So its behavior is entirely context dependent. Now, when the acid-base behavior specifically involves proton transfer, meaning the substance either donates or accepts a proton, we can use a more specific term, that term being amphoprotic. Amphoprotic substances are a subset of amphoteric substances, but not all amphoteric species are amphoprotic. That's because some acid-base reactions involve the exchange of electron pairs, not just protons. So only the ones dealing with protons fall under the amphoprotic category. The most common and important example of an amphoprotic substance is water. Water is an ideal example because it can behave like an acid or a base depending on what it's reacting with. If you add a strong acid, like hydrochloric acid, then water acts as a base and it will accept a proton and become hydronium ion. But if you add a base, water now behaves as an acid. It donates a proton and it forms hydroxide ions. So in both cases, water adjusts its behavior based on the chemical surroundings, which is exactly what makes it amphoprotic. Now that we've talked about how water can act as both an acid and a base, we're ready to cover a process called the autoionization of water. This is also sometimes referred to as autoprotolysis. This is a reaction that happens when water molecules interact with each other and exchange protons. So here's what's really happening. One water molecule donates a proton to another water molecule. That means one acts as an acid and the other one acts as a base. As a result, the water molecule that gains the proton becomes a hydronium ion, which we write as H3O with a +1 charge. And the one that loses the proton, that becomes a hydroxide ion, which we write as OH with a -1 charge. So in this process, two neutral water molecules react to form one positively charged hydronium ion and one negatively charged hydroxide ion. And this reaction is reversible, meaning that the hydronium and hydroxide ions, they can recombine to reform water. Since this is an equilibrium process, we can actually write an equilibrium constant expression to describe it. That constant is going to be called the water dissociation constant, and we use the symbol Kw to represent it. Kw is equal to the concentration of hydronium ions multiplied by the concentration of hydroxide ions. Now at room temperature, which is 25 degrees Celsius, the value of Kw is equal to 10 to the -14. That's a very small number, and it reflects the fact that only a tiny fraction of water molecules are ionized at any given time. In pure water, the concentrations of hydronium and hydroxide must always be equal since they're produced together in this 1-to-1 ratio. That means at 25 degrees Celsius, both the hydronium ion concentration and the hydroxide ion concentration, they're both equal to 10 to the -7 molar. This exact balance is what defines neutral water at 25 degrees Celsius. So it's really important here to emphasize that this value for Kw only applies at 25 degrees Celsius. Because the ionization of water is an endothermic process, the equilibrium shifts with temperature. So as the temperature increases, Kw becomes larger, and as the temperature decreases, Kw becomes smaller. And according to Le Chatelier's principle, heating favors more ionization, while cooling favors less. So what this means is that at higher temperatures, the concentrations of both hydronium and hydroxide increase, while at lower temperatures, they both decrease. Now here's the subtle but very important point. Even though Kw changes with temperature, water is still considered neutral as long as the concentrations of hydronium and hydroxide remain equal to one another. However, the pH value that corresponds to that neutral state is not always exactly 7 at temperatures outside of 25 degrees Celsius. So at 25 degrees Celsius, we define neutral as something that corresponds to a pH of 7. But at higher temperatures where Kw is larger, neutrality corresponds to a lower pH. At lower temperatures, neutrality corresponds to a higher pH. So neutrality is really about equality between hydronium and hydroxide ions and not about pH being fixed at 7. For our purposes in this general chemistry course, we will in fact focus on acid-base reactions at room temperature, where Kw is equal to 10 to the -14 and neutrality lines up with pH equal to 7. This is going to keep things easy, clear, and consistent. If we step outside of this framework, things get a lot more complicated. Now that we understand that Kw is equal to 10 to the -14 and how it connects to the concentration of hydronium ions and hydroxide ions, we can finally introduce the pH and the pOH scales, which give us a convenient way to describe how acidic or basic something is. Because these ion concentrations are very small decimal numbers, we use logarithms to simplify them. So the pH is then defined as the negative log of the hydronium ion concentration, and the pOH is defined as the negative log of the hydroxide ion concentration. At 25 degrees Celsius, pH plus pOH equals 14. That means if you know one value, you could always find the other by subtracting from 14. So for example, if the pH is 5, then the pOH must be 14 minus 5, and that is equal to 9. Also, there is something important I want to point out here. Whenever we refer to hydrogen ions, what we really mean is hydronium ions. So in aqueous solutions, free protons don't exist on their own. They're always bound to a water molecule to form hydronium ions. But by convention in acid-base chemistry, we often use the two interchangeably. H plus is easier to write, and laziness is but a normal human characteristic. So just make sure you understand that distinction. With that, let's jump into a couple of practice problems. Let's start with the first problem, which asks which statements are always true concerning Kw. We're going to work through each statement. Statement 1 says that Kw gets larger as temperature increases. Now, the autoionization of water is endothermic, so adding heat shifts the equilibrium towards more ions. And as temperature rises, Kw increases. So this statement is true. Statement 2 claims that Kw equals 10 to the negative 14. That numerical value is true only at room temperature, which means it's only true at 25 degrees Celsius. It's not a blanket statement. This is not always true regardless of temperature. So that's an important caveat to have added to this statement. So since that's not clarified, statement 2 is not true. Statement 3 states that Kw equals the concentration of hydrogen ions multiplied by the concentration of hydroxide ions. That is the definition of the water dissociation constant and is therefore always true. And remember that when we say hydrogen ion in water, we really mean hydronium ion, but we use those interchangeably in acid-base chemistry. So putting all of this together, the statements that are always true are 1 and 3, making the correct answer for this first problem answer choice A. The second problem says, what is the pOH of a solution that has a 10 to the negative 4 molar proton concentration? Proton concentration means the hydrogen ion concentration, which we treat as the hydronium concentration in aqueous solution. So the concentration of H plus equals 10 to the negative 4 molar. First, we want to convert to pH using our equation pH equals the negative log of the hydrogen ion concentration. The negative log of 10 to the negative 4 is 4. Next, we're going to convert that pH to pOH at 25 degrees Celsius using our equation that pH plus pOH equals 14. pOH equals 14 minus 4, which is 10. The correct answer is 10. That's answer choice A. Now, as a good habit, whenever you're given the hydrogen ion concentration, go straight to pH with the negative log, and then use pH plus pOH equals 14 to find pOH. Keeping in mind that 14 comes from pKw at room temperature, which is the assumption we work under here. Now that we've built a foundation with the different definitions of acids and bases, and we've talked about autoionization, let's turn to our next big topic, which is learning how to identify strong acids and strong bases. When we say an acid or a base is strong, what we mean is that it completely dissociates into ions in water. In other words, every molecule of a strong acid that you put into solution donates its protons, and every molecule of a strong base releases its hydroxide ions. There's no equilibrium to consider here because the dissociation goes essentially to completion. And this complete ionization is what makes them so powerful in controlling pH. So for strong acids, the dissociation is all about producing hydrogen ions, or more properly, hydronium ions. So when you dissolve something like hydrochloric acid in water, hydrochloric acid being a strong acid, it's not going to stay as HCl molecules. Instead, it instantly donates protons to water, giving you hydronium ions and chloride ions. And that's true for all of the strong acids on our list. The ones you need to memorize for this course are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, chloric acid, and perchloric acid. These are the acids that are going to dissociate completely, and they're going to dominate pH calculations when they're present in solution. Strong bases follow the same principle, except they produce hydroxide ions instead. Sodium hydroxide is probably the most familiar example. It is a strong base. You put sodium hydroxide in water, and it's going to separate completely into sodium ions and hydroxide ions. The other strong bases you need to know for this course are lithium hydroxide, potassium hydroxide, rubidium hydroxide, barium hydroxide, and strontium hydroxide. These also dissociate fully. In practice, because strong acids and bases are treated as 100% ionized, calculations are going to be super straightforward. If you prepare a 0.1 molar solution of hydrochloric acid, the concentration of hydronium ions is going to be 0.1 molar. So from there, you can calculate the pH directly as the negative log of 0.1, which equals 1. So the point we're trying to get across here is the concentration of the strong acid you have to start off with is going to be the exact concentration of hydronium ions because it will dissociate completely. Same principle for strong bases. If you instead prepare 0.1 molar sodium hydroxide, then the concentration of hydroxide ions is going to be 0.1 molar, and then you can calculate the pOH, negative log of your hydroxide ion concentration. This is going to give you negative log of 0.1, which equals 1. So the pOH is equal to 1. And then remember, you can always figure out pH by using the relationship that pH plus pOH equals 14 at 25 degrees Celsius. Now, the key point is that for strong acids and strong bases, the ion concentration equals the initial concentration because there is complete dissociation. So if you can keep that single sentence, that single point in mind, it will make calculations for strong acids and strong bases super easy. And this gives us a really simple framework for handling strong acids and bases. Of course, the thing to know is that it gets a little bit more complex, it gets a little more subtle when we move to weak acids and weak bases, where dissociation is incomplete. And there we would need equilibrium constants like Ka and Kb to describe the dissociation. That's what we're going to cover in the next lecture. But for now, let's test our understanding of strong acids and bases with two practice problems. The first question asks, what is the pH of 0.1 molar perchloric acid? Perchloric acid is one of our strong acids, which means it completely dissociates in water. Because the ionization is essentially 100%, the hydronium concentration is going to be the same as the initial acid concentration. So the concentration of hydronium ions equals 0.1 molar. And then to find pH, we're going to take the negative log of 0.1. That is going to be equal to 1. That is our pH. So the correct answer here is B. The second question asks, what is the pH of 10 to the negative 2.5 molar solution of nitric acid? Nitric acid is also a strong acid. So again, we can equate the hydronium concentration to the given molarity. That means the concentration of hydronium ions equals 10 to the negative 2.5 molar. The pH is the negative log of that value. So calculating that out, you're going to get that pH is equal to 2.5, and the correct answer is B. With that, we've completed this lecture. I hope it helps. Please let me know if you have any questions, comments, concerns down below. Other than that, I'll see you in the next lecture where we will discuss weak acids and weak bases. Good luck, happy studying, and have a beautiful, beautiful